spoke about the actual physical interpretation. The line integral was the area of the fence, but it's not a very useful interpretation. We're pretty much never going to think of it that way. But if you ask what is that number, that's what it was. But it's actually applied to other things. So we actually started 13.2, but we didn't finish it. So I'm hoping to finish that today and probably start 13.3. So let's see, where did we leave off? Okay. So we learned about line integrals over piecewise smooth curves, and that just means you just break it up, sum the integrals together. For each one you use the formula, and that's that. Now we're going to talk about line integrals with respect to the x and y component, right? Not with respect to arc length. So let's talk about that. So if I do the line integral along C of f x, y, x, right? So we're doing a line integral with respect to x. That would just be the integral from a to b. Right? So it's a very similar thing, except we're taking the derivative of the x term. And the definition for y is very similar. So that's that. And you would notice that the integrals that we did before, like back in Calc 1, if you think of this as parameterizing the x-axis, it actually goes right back to the Calc 1 definition of the integral, right? Because you would parameterize the x-axis as you could let x be itself, running between a and b, in which x prime would be 1. So your dt would just be dx, and your f of x, y would just be f of x, since there are no y's. Right? It essentially falls right back into the Calc 1 definition of the integral, so it is consistent. But this is, again, is a much more general thing, because your x of t, y of t can be any curve.
Wait, sorry. Can you repeat that? If with the f prime of t thing.
Come again?
With the x prime of t, can you repeat what you said?
I said it was consistent with the previous way we've defined integral in previous courses. If you looked at your curve, remember this is, again, for r of t equals x of t, y of t going from a to b. Right? I'm saying in previous courses, if this is actually consistent with the original definition, say, for example, think of an integral, like the regular integral back in Calc 1, f of x dx, as the integral along C of f of x y dx, where r of t is actually parameterized by x is t, y is 0, right? That will parameterize the x-axis, and t running between a and b. Right? So these works for general curves, including the familiar x-axis, y-axis. So for example, you could think of the integrals that you know before as a line integral over this curve with this particular parameterization.
Yeah, but what do you do with the x prime of t?
That would just be 1,
oh,
so
okay.
that
Yeah,
would be there.
Yes.
Right, so basically if you run through that, you get something like the integral from a to b of f of t dt, which looks pretty much like that. And so, but that's how we do it with respect to the x or y component, and now let's just do some examples. Let's say I wanted to compute, and this is actually a problem from your textbook. It's problem 4. Problem 4 in the section from the textbook. Integral along C of x e to the y dx. And C is the So we're going to do that. What does the picture look like?
So you have the e to the y, which is the exponential function. So basically, it's like ln of ln.
Right. You can solve for y. That means y is equal to ln x. So pretty much the curve you're looking at is ln x. But you want to start at 1, 0, which is here. You know ln x is 0 when x is 1. And it moves up to e, 1. Right? So you really want just this curve right here. Right? So that's your curve C. You're moving from this point to that point. Right? So that's the picture. And I want to compute this line integral. Yes?
Wait, so when you're parameterizing a curve like that, like you can do it in either of two ways. Like you can make y is as t and then x as e to the t, or you can make x as t and y is ln of t.
Yeah, yeah, you could do it in either way.
Either way, it doesn't matter.
No, you would get to the same answer. I'd stick with this one though. It's not.
Yeah.
E to the y is pretty easy to work with in general, especially with integral and derivatives. But yeah, that's it. So that's our picture, and let's just do this parameterization. So what is this? It's not a straight line. It's not a circle. It's a general curve. So we're going to do the thing where you just let one be a parameter and write the other guy in terms of the last variable, and this is already there for us. So I would just let y equals t and let x equals e to the t. Right? So I'm parameterizing with respect to y, which tells me what my t values run between, right? What would the t values be?
Well, solve for t. So from 0 to...
Huh? What would the t values be? 0 to 1, right?
Yeah.
T is y. Whatever the y values are in between is what t is going to run between, right? The y values are in between 0 and 1. Right? Since t equals y, right? Whatever y does, t is doing. T is y, right? So that's going to be our limits on our integral. That's our parameterization. So this would mean that y prime is 1 dt. This means that x prime is just equal to t, right? So x prime of t and y prime of t are the following, and now I just plug into that formula, right? So the integral along c of x e to the y dx is going to be the integral from 0 to 1 of my x is e to the t. My y is t, so I get another e to the t. My dx is e to the t. Right? So this guy here is x. This guy here is e to the y. This guy here is the dx. Right? The x prime dt. Okay? And the rest of this. Yeah.
You have r of t equal t comma 0, while the y component is 0.
Oh, this I was thinking of this familiar integral. This is along the x-axis.
Oh, so everything in y turns 0?
Yeah. I was just explaining that the familiar integral along the x-axis is actually consistent with these definitions.
Okay.
If you use your parameterization as the y is 0 for the x-axis and the x is just itself, the x is the parameter. Right? So it's just consistent. I was just showing that. Yeah, this is. Any questions? Yes.
Wait, so the physical interpretation of this, like, so basically you have
It's the same interpretation. The only difference is we are looking at the x as opposed to the arc length. So it's not a matter of computing in the context of
instead of
how far we've traveled is sort of what is the x component at this time.
So instead of the fence along the curve C, it's the projection, I guess, onto the xc plane, and then you do the integration.
Yeah, by the points on the x. Yeah.
Okay, so
So sort of, it's like what do you have to work with, right?
Yeah,
so if you
so-
know a lot about arc length, you do the arc length. If you know a lot about the x and y coordinates, you do it this
yeah,
way,
yeah,
right?
yeah.
And but that's more application. I'm not gonna. You're not gonna ever have to worry about that. You will be asked explicitly do it with respect to arc length or do it with respect to x or y. But in general, in practice, it comes down to actually what you know about, essentially. Right? You use whatever you know.
Well, we can do this problem the other way, right?
Yeah, why?
What do you mean?
This one, can we do it the other way?
Yeah, you can solve for y equals ln x. You can let then.
The way we learned last time with arc length.
Yeah, but it would be sort of a different thing. Yeah, you could do it. Yeah. It's not really the same as dx. You want to emphasize that you're doing it with respect to x. But yeah, those are just the formulas. You just apply the formulas. So you need to know the formulas very well.
So this wasn't really anything new, I guess.
Come again?
So this wasn't really anything new. We just use a general form.
Yeah, it's still this general formula except.
Do the integral, that's not it. Yeah, but it's just the same thing, but we're just doing the integral bit.
Yeah.
Yeah.
Yeah, a lot of it is just knowing the formula. Yeah. Right? There are a lot of times where you're going to have to actually do both, right? In this case, so that's just a notational thing. A lot of times if you have two integrals right by each other, they just might omit writing the second integral here. You're just supposed to know that an integral is supposed to be there. Right? So if it's along the same curve. Right? So you just can write one integral for the entire expression, but again, in each of these, you still follow the formula. All right, so this you're going to replace with x prime and y prime, and this you're going to use a parameterization for the curve C. Okay? Let's do an example of one of those guys. I'm going to type out here. Alright, so it's 3t. Anyway, parabolic arc given by y equals 4x squared from So we have to do with respect to both x and y, but the same principles apply, but we're just going to parameterize everything, find the derivatives, plug it in. Okay? So let's do that. How do you parameterize the parabolic arc? Yeah?
So you have the x is the t, and you have the y is equal to 14 minus
Yeah.
squared.
Right, so let x equals t, y equals 4t minus t squared. This means your dx would be dt. This means your dy would be 4 minus 2t dt. Right? Yes.
So just to be clear, you said from 2, 4 to 1, 3. So that's
Right, so what is the t value running between?
Does that indicate like a certain negative orientation or something? Like,
Yeah, it is orientation, which is another thing what I wanted to mention with this problem. So you can write this would be technically incorrect, right? Because this assumes that 1 is the lower bound, 2 is the upper bound. Here, you're going to want the t, you want to actually start at 2 and go to 1, right? So here's the start, which is going to be the lower bound,
So we should write it like that.
and here's the end, which is the upper bound, right? So it's not always bigger to smaller to bigger. It depends on orientation, which I'm going to make a note about it afterwards.
So we should write it like that then?
Hmm?
So we should write it like that then?
Yeah.
Okay.
So we're going to put 2 on the bottom, 1 on the top, essentially. Yes. So I was going to try to catch you guys in that, but you obviously pointed out. Okay. All right. So yeah. So now this implies the integral of c of y dx plus x squared dy is equal to the integral from, you want the t is the parameter which follows x. X starts at 2, ends at 1. So you put 2 here, 1 up there, and now you just plug and chug. The y was actually 4t minus t squared. Dx was just dt plus x squared. My x was just t, so x squared is just t squared times dy, right? And my dy is this guy. 4 minus t, right? Now the dt you can sort of think of as a common term. You can factor that out at the end. So this is really 2 to 1, 4t minus t squared plus t squared times 4 minus 2t dt, right? It's just a dt integral. And write brackets here. Okay? And now you just do that integral. So integral is a single variable, polynomial. So it's 4t minus t squared, multiply that out, 4t squared minus 2t cubed. Combine the squares. So, what's the integral? Integral of 4t? Integral of this? Integral of that?
Q to the 6.
1 half 2.
And we go between 2 and 1. So if you plug in 1, you get 2 plus 1 minus a half minus open bracket. You plug in 2, you get 8 plus 8 minus 8. Right, so this is 2 plus 1, this is 3 minus 8, that's minus 5, minus a half.
So we likely will not get such an easy problem like this, right?
Come again?
So we likely won't get a polynomial integral.
You might.
Really?
Yeah.
Okay.
Yes.
Question. Why did you only choose to use the bounds 2 to 1 and then just split it up as 2 integrals?
Why did I use the bounds?
2 to 1 and instead of you didn't split it up into 2 integrals because one is in terms of x and the other is in terms of y.
Right, so it's actually the same C for both.
Yeah.
That was the idea. So I only had to do parameterization once,
Okay.
and it will actually work out. So I did actually apply the formula twice, right? For the first integral, I should attach an x prime, which I did. And for the second integral, I attach a y prime, which I did. Right? I'm just doing both of them simultaneously, right? And you can do that. Right? It's the same curve, so you don't have to set up two separate problems, because really the parameterization is going to be the same. So you just do it all in one anyway. Okay? Yes.
How did you determine that the 2 was the lower bound and 1 was the upper bound?
Oh, because of the important way they described it. We're going from this to that. It means that this is the start, that's the end. And your limits have to account for
With
that.
respect to x?
Yes, with respect to x.
So we have a negative area somewhere.
Yeah, it could be the curve underneath. So, yes, so when you're on the integral, the limits always go from start to end. So it's not always smaller to bigger. You have to really read the question, know where am I going from, which point am I starting to which point am I ending, right? And it's going to determine it's done, which is what we call orientation, which is what I'm going to talk about now.
For the vector field, you mean?
Come again?
Because orientation matters as a vector, and vector fields too.
Yeah, we're going to talk about orientation in 3-space as well, but for now I'm going to talk about orientation as far as curves are concerned, because we will also be doing curves in 3-space. So let's see. Called orientation, right? For a curve, this means the direction in which you traverse the curve. So talk about the direction you're going in when you're traveling around the curve. And in the cases of closed curves, they are specific distinctions. Right? If your curve is closed, right? Closed means the start point and the end point are the same, right? Just go in a loop and end up where you started. Then the counter-clockwise direction is called the positive orientation. The clockwise direction is the negative orientation. So they might describe the direction you're moving in by the points. They might say, we're going from here to here. But if your curve is closed, they might just say, oh, it's positively oriented, or it's negatively oriented. And you should know that you should be switching from counterclockwise to clockwise.
So this is where the right hand rule becomes important?
No, right hand rule.
Okay.
This is just a convention. It's just a way for them to convey the information that they want to convey, right? If you're going around something in a counterclockwise direction, so you have a closed curve, and you're moving around the curve in this way, this is positive orientation. So you have the same curve, but you're going around in the opposite way. This is negative orientation. Right? It's just the way they call it. Another thing about orientation is, as far as calculations are concerned, it only negates your integral. So if we have this guy, then writing a negative c down here means you've changed the orientation. Moreover, integral on c of f of x, y, s is equal to the negative. So if you switch orientations, you actually negate the answer, right? That's going to be another important thing. So let's see. So this is we have this for example. Then switching the orientation actually reverses your orientation. However, right? But this one really switches because you're talking about x and y. Your x and y can actually change, right? You can actually decrease the x or increase the x. But when you're talking about arc length, it's just a length. There is no such thing as measuring a length in the opposite way, right? Length is not a quantity that has direction, while the x can have direction. So if you have this guy with respect to arc length, he's actually exactly equal to, if you reverse their orientation. There are proofs for this, but I won't go into them, but you realize that if you actually do this, it will always end up being the same. Whereas if you do it with a dx or a dy, it actually changes. You have to actually negate it. So it also depends on the kind of integral you're doing, and this sort of shows you the difference between how, with respect to arc length, can change with respect to x and y. Because length doesn't have a direction. X and y has direction. Let's do another example. So that's just some theory, giving you some background. Because when they're telling you the questions, they're going to mention all these words. They're going to say positive orientation or negative orientation. I'm just explaining what these mean. Right? So it's just a definition. It's a convention. There's no real mathematical meaning to it. They just decided this is the way it's going to be. Follow these rules whenever we ask you a question. Right? And that's what it is.
Question.
Yes.
The negative c. What do you mean by the negative c? Like the
You've changed the orientation.
I know, but I mean the negative c. The c is like the bound,
The c is the curve.
the curve itself.
Yeah. So if I called this c, I would call this negative c. It's the same curve, except I changed the way I'm going around it.
Okay.
So if it's not a loop, then it's just going one way is negative, the other is positive.
Yeah, so if I have this is c with the given orientation. Then if I have the same curve with the opposite orientation, I would call that negative c. Right? Now, this is not positive or negative because it's not a closed curve, but it's just whatever you're given. If you're reversing direction, it's the negative, and you call that the negative orientation. Yes.
So it actually becomes negative though through the limits integration, right? And you would just reverse those two?
Yeah, essentially that's what happens, right? What happens is if you reverse the direction, your start point and your end point switches, and switching the limits on an integral actually negates the integral. So yeah, it's actually going right back to the properties of integrals, so you can look at it that way as well.
Wait, so you said with respect to arc length, the orientation is relevant because it doesn't have any direction.
Yeah, length doesn't have a direction.
So like, but if the infinitesimal ES element is like represented like with a vector, how does that work?
It's not a vector. ds is a scalar. There's going to be one where we have the ds as a direction, but that's the s would be a vector itself. Here it doesn't apply.
So it's always positive.
Yeah, because no, I never said it's always positive.
I mean, no, I mean.
You can do this and get a negative answer. I'm just saying if you went in the opposite direction, you get that same negative answer.
Yeah.
It won't change.
But isn't ds just the magnitude of r prime and t, so it should be always positive?
Yeah, but what about your f? Your f has no.
Oh, f is not.
F doesn't
but
always
ds
need to be
is always-
positive. Yeah. So the sign would depend on the f. The thing is, if you change the direction, it won't change. If you're going with respect to x or y, it will. But you don't have to like set up the problem with a reverse orientation. Just negate the answer and it will work. Okay. Yes.
So with the minus c, you would get a negative length.
Come again?
On the arc length, on the right hand side, with the minus c for a curve, would you get a negative answer?
You could.
No. So.
Okay, we can generally know if it's a loop by if it has any trick in it, like sine or cosine. We know to loop that.
No, you know it's a loop by what they tell you. They'll always describe it. They'll say this is a closed curve, or this is a circle, or this is a quarter of a circle. You know if it's closed or not, especially after you draw the picture. So it all comes down to really paying attention. So skip that example and move to this one. Here's a final example. Note. The above actually generalizes to 3D. So for example, someone could ask you the problem of integral along c of z dx plus x dy plus y dz, right? Where c is the line segment from 1, 2, 3 to by far, most of the things I say here in 2 dimensions, I've always generalized to 3 dimensions. That will very usually happen. So Yeah, so you could throw in a z in there, but it's still going to be the same process. You parameterize it, and you plug in the pieces, right? So let's do this one. How would you parameterize the x?
So yeah, x naught plus the final
So 1
times
plus-
t. So 1 plus
1 plus 2t.
2t.
1 plus 2t, y,
2 plus 3t.
2 plus 3.
2 plus 3t, z,
3 plus 4t.
3 plus 4t, and your dx would be 2 dt, right? Your dy would be
3
3
dt.
dt, your dz would be 4 dt. So our integral along c, and to save writing, sometimes I just write the integral there. I know formally it's not correct, but it's shorthand, and it's very common to do that. So you can say the integral along c is equal to, what's the t limits?
0 to 1.
0 to 1 whenever we use that formula, right? 0 to 1 of z, which is 3 plus 4t, times dx, right, which is just 2, plus y, plus x, which is 1 plus 2t, times dy, which is 3, plus y, which is 2 plus 3t,
Times 4.
times dz, which is 4, and I can put the dt at the end.
Just add them up and then.
And so now you're just going to 6 plus 8t plus 3 plus 6t plus 8 plus 12t. What constants do we have? 6 plus 3 is 9, plus 8 is 17. 8 plus 6 is 14,
26.
plus 12 is so this is equal to 17t plus, and this is what, 13t squared? It's just 17 plus 13. Any questions? Just applying a formula over and over again. Slightly different context, but it's always sort of the same thing going on. They're going to give you an integral, they're going to describe the curve. It's going to be a straight line segment, or circular arc, or any other random curve in which you do that last trick. And after you set that up, it's just back to Calc 1. Right? Or Calc 2, depending on the integral. In your homework, there are going to be problems you have to do by parts and trig substitution. All that you still have to remember. Right? I'm just doing simple examples to show you how it's done. Okay? Any questions? Okay. Integrals like fds, fpx, dy, sometimes. Line integrals over scalar fields, that's because your f is a scalar function, right? Which, of course, that suggests it's possible to take line integrals over vector fields, which is what we're going to introduce now. So that's everything you need to know about line integrals over scalar fields. Pretty much one sort of general formula. Well, for the ds has one formula, for the dx and dy has another formula. You just apply these formulas, it takes you back to Calc 1 or 2, and you're done. And of course, you can combine them, but whenever they are combined in this form, it just means it's the same curve, so the same parameterization works for everyone. You just do everyone at the same time.
So, like, you said line integrals over scalar fields. So by that, do you mean like you're
I'm integrating a
over
scalar function here, and the dx is a scalar multiplication.
So you're referring to the actual field you're integrating, not over the domain of integration.
No, the actual function I'm integrating, the integrand, is a
Wait,
scalar.
But so is the domain, since the domain is also one-dimensional, could it be considered a kind of like a scalar field? Since,
Not really, no. It's based on the function you're integrating.
so the domain doesn't have any.
No, that's not where the name comes from. It comes from
Okay.
the function, right? And we're going to see the difference in that now. So, just to make a definition. Let f be a continuous.
This is all in 13.2, right?
Yeah, we're still in 13.2.
Okay.
Right? So remember, when we're talking about scalar fields, I always draw the arrow over it. Your textbook might make it a bold letter. That's how you know that they're talking about a vector as opposed to a scalar, right? So in print, you might see bold letters. Usually when you're writing, you write a little arrow over it, and that means I'm talking about a vector field, which means your function is actually a vector now, and it has components. So we have a vector field defined on a smooth curve C, which we can parameterize. It's given by R of t. For t going between some limits. Then the line integral is given by the following. This is the notation f dot dr. So if you see something like this, f dot dr, that means you're taking a line integral over a vector field, right? R is describing the curve that you're going along, f is the function, right? Has to be continuous because we're going to be taking derivatives and integrals and stuff. And this is actually what it means. So f dot dr really means this thing. So within your vector function, you're going to plug in the parameterization that you get from your R, multiply by the derivative. It's a dot product now because we're dealing with vectors. And that's when you work out the dot product, you're going to get a regular integral that you do. So
you dot it with the.
you dot it with the derivative.
Yeah. So some other magnitude in one.
It's, no.
Yeah.
But your answer will be a scalar since a dot product is a scalar. And we're going to talk about, I will mention what this is. The interesting thing about this integral is that it gives you work in the physics sense, right? That is integral along C of f dot dr equals the work in moving a particle or object along C through the field F. Okay. So the interpretation of this integral is work. So a lot of times they might ask you the question, oh, find the work in moving a particle from this point to this point in this vector field. You should know, you should be computing the f dot dr integral.
So we'll do that in our
Right?
test.
So it's synonyms, yeah.
So the F is force.
The F you can think of as force in a sense, yes. It's the external force, what's going on in the environment.
And dr is our displacement.
And dr is the curve, the path you're traveling
So
along.
displacement, okay. So basically, we are going to have to do that in our exam, basically.
Yeah. So I might mention f dot dr explicitly, or I might just say find the work, and I expect you to know this is the integral you're supposed to compute. So that's what this integral is good for, and let's do an example. Example. Find the work done So for these you don't need to draw a picture, but you might recall this field. It's one of the first ones I gave you an example for in 3.1. It's just that guy that goes in a circle. Right? And we are traveling along the curve y equals x squared minus 1. So there's a curve in this field, x squared minus 1. And we want to travel from minus 2, comma 3, and end up at 1, comma 0. So this is our curve C. So your field could look like this, and we say, oh, it could represent something like water, you know, a whirlpool or something like that. So basically there's like a whirlpool, and we're here, and someone is drowning over here, and we want to figure out how much work would it take to actually save his life if this is the safest path to travel along. You know, is it really worth all that work? Well, we'd have to compute the work to find out, right? So what we're going to do is figure out how much work is going to be done to move from this point to that point if the external forces around us are according to this vector field, right?
So doing that, we can see it's humanly possible to say that.
Yeah, or you know, fiscally smart, whatever, economical. So yeah, we know that work equals the integral along C of f dot dr. So what are we going to need to do? We're going to find the r, differentiate the r, plug in the f, and integrate. Right? So here, rt equals How would I parameterize this? Yeah.
As x is equal to t and y is equal to t minus 1.
Okay, what are my t values?
Okay, so you go from t is -2 to 1.
Right. T goes from -2 to 1, right? Because it's following the x values. So t goes from -2 to 1, and then what we're going to do, we're going to find the dr, which is going to be what?
1 to t.
1, 2t dt, and we can find the f of our t, which means you pretty much go to the f and you're going to plug in the parameterization, right? That's what that means. So f is y comma minus x. Your y is actually t squared minus 1. So this is y comma minus x, right? So this guy here is y. This guy here is minus x, right? And that we get from this guy, right? This is x of t, y of t. Right? So you go back to your function, you plug in the parameterization, and now you just integrate. Which is why on quiz 1 I asked you to do your dot property, because you're going to need to know how to do that. So this is going to be what? T squared minus 1
Plus
minus 2t squared dt. So we have minus the integral from -2 to 1 of, this is 1 plus t squared. So 1 minus a third, well, this is 1 minus a third plus 2. So this is 3 plus 7 over 3, which is, is that right?
So it wouldn't
Is that
take
right?
any work to rescue?
No, we'd actually save. Looks like the force field would do most of the work for us. Yeah. Right. I don't remember getting that answer when
I think,
tried to-
isn't it 1 plus 1/3 there, not minus 1/3?
Yes, it's a plus, yeah.
Plus 1/3.
Yeah, so that would give me 9 over 3, which is just 3.
Yes.
Yeah.
So that's
So still negative 6.
Yep.
So you can save yourself.
Yeah, we still save work. So yeah, I guess he's worth saving.
Do you need to do this in this section or no?
No, I don't care.
Okay.
First,
Yeah.
determine R on this place. Couldn't we just parameterize from the two given points instead of like setting x to be t,
What do you mean, parameterize how?
like the given point -2, 3 to 1, 0?
How? By-
Just asking that question to determine find R.
You mean using a formula, or what do you mean?
Like
Well, R is going along this curve from that point to that point. See what I'm saying? So it's not a straight line, it's not a circle, so I can't use those formulas. So I decided to parameterize in terms of the independent variable. X is the independent variable here, so I just let that be t and write y in terms of that.
Hold on. So you said this is the work done by the force field, that integral, that's what it represents?
Yeah.
Or- So if it's negative, isn't it work done against the force field? Because the force
Yes. That's, so you notice that if you're traveling here, a lot of your arrows are fighting you. Right. So that's how you can sort of interpret it.
So,
You're going against the curve.
yeah, so you have to go, so if it's negative, that's work done against the field, and
Yeah.
work done by the field has to be positive.
Yeah. But like I said, those considerations we don't really care about here. I'm just teaching you theory. But yeah, if you're doing this in a physics class, then those considerations would be important.
So you just want the number basically.
Yeah. So we don't care about units. We don't care about what direction it's going. I don't care. Just give me the answer. That's the question. Yeah. So in later classes, those would be important. And I would hope your professor would tell you about all those things. Let's see. Here's something of note. And then we will, I guess we can finish after this. It's not a problem, it's just something to realize. Suppose that f is equal to some function, right? P, Q, R. Right? So these are, functions of x and y. Right? P, Q. Okay. And take R of t, R equals x, y, z, right? Just the canonical representation of some curve where you're representing by the coordinates, x, y, z. Now, then, what would f dot dr look like?
I mean, P, Q, and R are functions of x,
Yeah,
y,
they're
and
just
z.
functions, yeah.
Of x, y, and z, or just x, y?
X and y. How would it look? Well, this would look like the integral along C of the f is the p, q, r, right? Of course, you're going to plug in the parameterization. Dot product with, what is that going to look like? That's close. Derivative of x, remember this is a function, right? So I'm not going to write 1, I'm just going to write dx to be the derivative of whatever the x component is. I can write this to be dy, the derivative of the y component. I can write this to be dz, the derivative of the z component. If I take the dot product, what would that look like? P dx plus q dy plus r dz. Looks familiar? All right. So when you see an integral like this, one interpretation could be it's figuring out the work for something. And this is why in nature, these integrals show up all the time, which is why I had to introduce them. Okay? And with that, we close. Are there any questions?
So we just solve the integral like we did before.
Yeah. So there might be times where, think of it as one where the other can make things easier. You probably have some homework problems that.
And when are you going to switch to, when are we going to switch books?
Oh, whenever according to the syllabus. I don't know exactly when. Class, the third week to the end of class.
Really?
Or something.
And end class?
The linear algebra part is not that hard. It's not going to be that long. Huh? So this is actually finished. So 13.2 is due next class, and I'll probably give you a quiz on this stuff.
Any class quiz?
Thank